So this is kind of an intro into Earth and space science, and also chapter 1. A lot of these things we'll talk about more in depth later on in the semester, but this is just kind of a quick overview, introduction kind of thing. Just kind of put some of this into your head so you can kind of have it knocking around in there for a while.
Do we gotta write this down?
Do what?
Do we have to write this down?
No, I mean, you don't have to write it down. I mean, if you want to, you feel free, but you don't have to. Like I said, these will be up on YouTube.
All right.
Is this stuff like, is it gonna be like on a quiz or something?
Yeah, I mean, this is the material that'll be quiz and test material. Yeah.
Okay.
Like this stuff, and then material that's in the assignments and things like that. Yeah, I mean, this is the important information that's going to make that stuff up. All right, so Earth and space, it's kind of self-explanatory just by the name. I mean, obviously there's some Earth and there's some space. And there are lots of different branches of science, but the 4 main branches of science that kind of contribute to include the information that kind of forms Earth and space science. First one is geology. So study the surface and interior of the Earth. A lot of times people think of, or they hear geology and they think it's just studying rocks, which it's not. And that's part of it and can be part of it, but certainly not all of it. The study of rocks specifically is another branch of science called petrology. But geology in general is just the study of the Earth, what it's made up of, how it forms, how it changes, things like that. And then there are obviously branches of geology that are more specific. Like I had a friend whose dad, in high school, his dad was a hydrogeologist. So he studied how water affected rocks, basically. So there are more specific ones. The next one, astronomy. So the study of the universe. So anything that's in space is going to be included in that. Planets and stars and galaxies and black holes and pulsars and quasars and comets and asteroids and all that. That will all be included in that. And we'll get into space and astronomy after spring break. Will be about the time that we'll get into astronomy. And I think I mentioned it in here, I can't remember, that Mr. Shackelford, one of the other Earth and space teachers, he now has an astronomy and geology class. So it's 1 semester of each. So maybe for next year, take a look at it if it's something that interests you. The third is meteorology. So it's the study of the atmosphere. When you hear meteorology, and anybody, where have people heard meteorology? Has anybody heard that before?
Hello.
The news? What specific part of the news?
I haven't.
The weather? Yeah. Meteorology, they study the atmosphere. And since weather takes place in the atmosphere, a meteorologist, is the person that is on the news and tells us about the weather. They study the weather, they predict the weather, all those things. So, I mean, it's pretty useful stuff. And then the last one, which we really won't talk a lot about, is oceanography. So in the study of the ocean with oceanography is more of the study of the ocean itself, not so much the life in the ocean, which is getting into more marine biology. But the ocean water, what makes up ocean water, formation, how it changes, the ocean floor, processes that go on there, but not so much the the light that's in the ocean. We don't really study anything in Earth and space science that's alive now. We'll talk a little bit about fossils and some things like that, but that stuff's long been dead. So those are the four main branches: geology, astronomy, meteorology, and oceanography. Talk a little bit about systems. Two different types of systems. We have open systems and closed systems. So for the open system, the example is an island. In an open system, both matter and energy can come into the system and go out of the system. So physical stuff can come in and leave. So with this island as the example, rain could fall on the island, a bird could fly in, a bird could fly out, things could wash up on the shore, things could get in the water and leave. Things can move in and out. Matter can. Energy also can as well. Radiation and light from the sun can come in and hit the island. Some of that could be reflected back into the environment. So that's energy moving into the system and out of the system. Closed system is a little different, where we have a little research submarine as an example. In a closed system, matter can't move in and out of the system. And I know some submarines have things where, things can go from outside, inside, and back and forth. But for this example, with this little one, it's all sealed up and self-contained. So whatever you're gonna need, you better have, because you can't get any other food once you're down there. You can't get any more air, which that's a big one. You better have everything that you need. Energy can be transferred back and forth though. And depending on the temperature of the water, that's going to affect the temperature, inside that submarine, which as you go deeper and deeper, it gets colder and colder. So the energy can move in and out, but matter can't. So it's a closed system to matter moving. Energy is going to move regardless, but the matter, that's a whole different thing. So, and anyone can answer, what would the Earth be? Would the Earth be an open or closed system?
Open.
Yeah, it would be an open system. And the Earth hasn't always been an open system, but now that we can send things into space, and we're moving matter out, then yeah, it's an open system. Moving energy out, and that's easy. Sunlight's reflected off of it, or radio waves and things like that go out into space. So that part's the easy part. But yeah, good. The Earth is an open system. Right. So where we are located here on Earth, this drawing is obviously not to scale distance-wise between the planets, thankfully. But the order of the planets is correct, and the relative size of the planets to one another is accurate, just not the distance between them. So this is our solar system. Our solar system is part of a galaxy, which, what's the name of our galaxy?
Milky Way.
Good, Milky Way. It's usually right next to the Snickers and the Twix, Butterfingers sometimes. That's our galaxy, Milky Way, which for whatever reason, galaxies tend to be grouped in what we call clusters, and that's in the universe. The universe has everything that we know of that exists. So going from solar system to galaxy to cluster to universe is going from specific to very broad. You kind of think of it kind of going the other direction, starting a universe. If we were talking about where we live, we could say, we live on Earth, in the United States, in Indiana, in Indianapolis, or something like that, as you're becoming more and more specific. Okay, so the Earth's spheres. Sure, we all know a sphere, something shaped like a ball. In this usage, we're not necessarily saying that it's shaped like a sphere, but that it includes everything. So the four spheres, the four Earth spheres, the first one is the geosphere. So that's all the stuff that makes up the Earth. So rock, metal, minerals, soil, sand, all that stuff. That's all geosphere. All the things that make up the Earth itself. And the second one is the hydrosphere. Who has an idea of what that would be talking about? What does hydro mean as a prefix? Anybody?
Water.
Good. Water. Anything with hydro on the front has to do with water, like hydration or dehydration. Hydro means water. So the hydrosphere is all of the water that is on the surface of the Earth, that's in the Earth, and what's kind of often forgotten is all the water that's in the atmosphere, because there's quite a bit of it if you were to put it all in one place. So fresh water, salt water, above ground, below ground, all that stuff. Ice, snow, that would all be included in the hydrosphere because that's just all the water that's on Earth. Next one's the atmosphere, the thin layer of gases that surround the Earth that allow us to breathe, which is pretty cool. Protects us from a lot of the sun's radiation. Protects us from a lot of debris that flies through space, that is burnt up and destroyed in the atmosphere before it hits the surface. Helps us out. So thank you, atmosphere, for letting us live. And then the last one is the biosphere. So the biosphere is all living things on the Earth, in the Earth, from blue whales to bacteria, plants, bugs, everything. Anything that's alive is included in the biosphere. Those are the four spheres, or four Earth spheres. And kind of break down the words a little bit. Hydrosphere, hydro meaning water, atmos, vapor or steam for the atmosphere, geo meaning earth, and then bio meaning life. So just kind of broke it down there a little bit. All right, so as far as kind of just a very brief history of kind of where the Earth came from, how it formed. The first thing that happened was the formation of the planet itself, and that's through something called the nebular hypothesis. The nebula is just a huge cloud of gas and dust. When I say huge, I'm talking the size of the solar system, kind of huge. Over time, that cloud starts to rotate, and then those little pieces of dust start to stick together as they come into contact with one another, and then it builds up and forms planets with a sun in the middle. So it's kind of the reigning theory of how the planets formed. Elements are also forming at this time, and as far as we know, pretty much all the elements that we know of were formed in stars through a process called fusion, which that's how the sun produces energy. It's a type of nuclear reaction where atoms are fused together, they're joined together. So that the sun uses hydrogen and it fuses those hydrogen atoms together, which releases energy, and then it creates helium atoms. The nuclear process we use in like power plants and things like that is something completely different. It's called fusion, or I'm sorry, fission. It goes the opposite direction. So in fission, you start with a big radioactive element, and it breaks down into smaller stuff. Then you end up with, you know, toxic and radioactive waste that's difficult to deal with and very dangerous. Whereas fusion, you end up with helium, the same stuff that you put in balloons and makes you talk funny if you inhale it and all that stuff. We can't do fusion on a large scale. We don't have that technology at this point. Maybe someday, but not yet. So that creates elements, though, because as the stars use up all the hydrogen, then they start fusing helium together, and that forms different elements. And then when it uses all that up, it starts fusing different things, and it forms different elements. Right. So after the Earth itself forms, everything that is in the Earth and makes up the Earth was liquid. It was so hot that everything was molten. And that led to the formation of layers because of the different densities of the materials that make up the Earth. So the most dense materials, the heaviest materials, like the metals, sank to the center of the Earth. So that's why our core is metal. And then the lighter materials that are made of rock and all that, that's basically went to the surface. So that's why the mantle and the crust are made out of rock. Now there's still metal in the, the mantle and the crust, but it's not, solid metal like the core is. After that, after the outside cools and hardens, then we start to have formation in the atmosphere. It's thought that gases from volcanic activity was the main contributor to the atmosphere forming. After that, we have formation of oceans, which allowed the plants to grow, or to form and grow, and then eventually animals after that. And this last one, there have been several things that have happened to the Earth, cataclysmic events that have changed all life on Earth, or eradicated all life on Earth, pretty much. And it's certainly not to say that it won't happen again. I mean, it's more of when versus if. It will happen. It's just a matter of when it'll happen. I'm not trying to keep people up at night, but it will happen eventually. All right, the Earth. Some people might disagree with this, but the Earth is a sphere. Just like in this picture, for whatever reason, in the last few years, it seems like more and more people tend to think that the Earth is flat versus a sphere. I don't know. I haven't really heard anything that has convinced me that it's flat. One little piece of evidence is ship's mast. So if you're standing on shore and the ship is going away from you towards the horizon, as it goes over the curvature of the Earth, you won't see the body of the ship, but you'll still see the mast as it goes over. Or just like, if a car is going over a hill, it's the same principle. Another one is constellations. So there's some constellations, there's some stars that are only visible from the northern hemisphere. Or there are some constellations and stars that are only visible from the southern hemisphere. And that's just because you can't see around the Earth to see all the constellations. So it kind of tells us that it is spherical. Another one is eclipses. So this one is a lunar eclipse. So the moon is passing into the Earth's shadow. So from the Earth's shadow, we can see that it's round. Of course, you don't get any depth to it, but you can see that it's round. And then now, since we're able to put people into space and satellites and things like that, and people can orbit the Earth, and now we can see that it is spherical. Although, like I said, some people might disagree. I mentioned weight, I think yesterday when I was talking about mass, and the fact that weight is just a measure of gravity pulling down on whatever it is, and that being measured. Gravity depends on two things: the size of the object and the distance, between the objects. So the bigger objects are, the more gravity, and the closer they are, the more gravity. So if something is really big and really close, there's a lot of gravity. If something's really small and far away, there's not much gravity at all. Since with the Earth being right here, gravity pulls us towards the center of the Earth. And since the Earth isn't perfectly round, or it's not perfectly spherical, it's a little bit squished. The distance to the center of the Earth is a little bit further if you're on the equator than if you're at the North Pole or South Pole. So if you're on the equator, you had a super sensitive scale, you would actually weigh less than you would at one of the poles. Just like if you weighed yourself at sea level and then you weighed yourself at the top of a mountain, you would weigh less at the top of the mountain because you're further away from the center of the Earth. So there's not as much gravity pulling on you. And it's not a huge difference. I mean, it's not huge at all, but it is something that's measurable because there is a change in that distance. And this shows the values for the diameter of the Earth across the equator, 12,756 versus the diameter from pole to pole, 12,714. So, especially on something the size of the Earth, not a big difference, but I mean, it is a difference. There is a little bit of a difference. So the actual shape of the Earth is something we call an oblate spheroid. So spheroid because it's basically, the same form as a sphere, but it's modified a little bit. It's, like I said, it's kind of squished down a little bit. Does anybody have an idea of why it might kind of bulge in the middle and might kind of be squished down? I mean, obviously something didn't squash the Earth. But does anybody have any ideas about why it might be a little bit, kind of bulging in the middle? Maybe think about what the Earth does all the time.
Oh, it spins.
Good, it rotates. So the Earth is rotating all the time, and it was rotating when the Earth was molten as well. So as you know, as things spin, things want to move out from there. Like if you're on a merry-go-round, you're spinning, you can feel that force pulling you out. So when the Earth was molten and everything was liquid, it wanted to flatten out, but then it also had gravity of everything it was made of holding it in. So you got kind of a distortion there, and then things cooled and hardened. So this is kind of and it's still spinning. So we kind of have this shape now of that oblate spheroid. Pretty much a sphere, but a little bit off. And we'll talk more about the Earth layers. This just kind of shows the layers: the crust, mantle, the outer core, and the inner core. And again, the main reason that we have those is density and differences in density. And you can look at the differences in the densities. You have the most dense material in the center and the least dense on the outside. And the crust and the mantle are mostly rock. So the densities are pretty similar, but then the outer core and inner core are metal, which those two are similar, but there's a huge difference in those densities because the first two are rock and these are all metal. We don't have any other layers that are like pop or hip hop, just rock and metal. Sorry. And this is just the average density of the Earth as a whole, putting them all together. The Earth's interior heat. So the inside of the Earth is hot. And the deeper you go into the Earth and the closer you get to the core, the hotter it gets. That heat, some of it is left over from the nebula. It's left over from when the Earth first formed. Kind of like if you cook something in the oven or you microwave something, you take it out and the outside can cool down pretty quickly, but the inside's really hot. Like, like some pizza rolls or Hot Pocket or something is notorious for this. You think it's okay, and you bite into it, and it's crazy hot, and it burns your tongue on the top of your mouth, and it messes up your whole day. Kind of like that. This is still heat that's left over from when it first formed, when everything was molten and liquid. The second one is radioactive elements that are in the Earth. So these radioactive elements are giving off radiation because that's what they do, and that radiation heats up, the surrounding rock. And since that stuff is already warm, it just keeps it warm. So it's kind of like there's a microwave down there that's kind of keeping it perpetually warm. And eventually it'll cool off, it is cooling all the time. It's just not very much. Plus, this is a huge hot pocket. There's a lot of heat trapped inside the Earth. So it'll take quite a while to cool off, but it will happen eventually. And this third one, friction. The first two are definitely the main ones. This is just friction between plates, tectonic plates as they're moving and being forced down into the Earth and things like that, which cause earthquakes and all that. But compared to the other two, this friction is pretty minor. So I really wouldn't worry about that one. Just kind of the, leftover from the Earth's formation and the radioactive elements would be the two main ones on that one. I should probably just take this third one off. Yes, that's what I have on that. Does anybody have any questions? Are there any slides I need to pop back to? Okay, seeing none.